everyone. Good morning. Thank you for the introduction and thank you to the organizers for giving me the opportunity to speak this morning. So I am Khadijat and I'm a third year PhD student in the Department of Mechanical Engineering. And I will be giving a short poster presentation on how acoustic emission signals can be a diagnostic tool for joint wear. So first, a brief background. What is acoustic emission? Acoustic emission testing is a non-destructive testing that can be used in the detection of the onset and progression of mechanical flaws. As illustrated in the diagram on the right, when you have, for example, an implant with a load on it, so the effects of the load pressing on the implant would create some sort of flaw in the system. For example, you could have it pressed down, and this would lead to a bit of stress and strain energy that is developed, which is then picked up by an acoustic emission sensor. And then this sensor converts the mechanical strain energy to electrical energy, which is amplified and processed and then acquired in the acquisition system. The final AE signal will then be recorded as a waveform as shown in this diagram here. Since acoustic emission, since the inception of the system, since around the 1950s, it has been used to look at friction and wear patterns in mechanical systems. For example, wear in transmission systems, such as gears, and also for machine tool monitoring. More recently, it has also emerged as a diagnostic tool for the assessment of human joint and orthopedic implants. In case of human joint, it has actually been used to differentiate between osteoarthritic knee and healthy knee joints. This actually is an exciting finding to show that maybe we could be able to actually diagnose osteoarthritic knee very quickly and prevent the advanced development of the injury. And also, it's also been shown that it could be used to predict bone fractures. It's also been used in implant condition monitoring and comparison between a test of when the implant is in the body and outside of the body when it has been retrieved has shown that there is a way that there is a potential for us to be able to look at implant condition monitoring and also by extension to actually diagnose the failure of the implants. But for us to be able to actually achieve this potential of acoustic emission, we would have to be able to analyze the signals in a way that we can differentiate between failure processes. That led to the aim of this work, which is to use supervised learning to see how acoustic emission signals can be analyzed to differentiate between wear mechanisms. The methodology is split into two parts. So we have the acquisition of the signals and then the classification of the signals. For the acquisition of the signals, a biotriboacoustic test system is used to acquire acoustic emission signals from two simulated wear mechanisms, adhesive and abrasive wear. So for the adhesive wear, we have a smooth pick rod that is sliding on a smooth stainless steel, as shown in this diagram here. For the abrasive wear, the stainless steel was first roughened using a P40 abrasive paper to create sharp obtrusions on the surface, which will allow abrasion to take place. And also to prevent adhesion from taking place, a lubricant of rain gas solution was also used for the test. The test conditions were calculated using controlled joint conditions and using a spinal lumbar implant as the exemplar joints. The test involved two different equipment. So we have the tribometer, which is a rig that is used to measure friction in two materials that are sliding over each other. And also, as you can see with the AE sensor, this sensor is then connected to a computer, which is a system that acquires the AE signals and processes it and records it in form of the waveform. After testing, the AE hits from adhesive and abrasive tests were then compiled, and also all the features were extracted and used for processing for the classification. So for the classification of the AE signals, the first feature extraction took place using principal component analysis. This is a mathematical technique that is used to determine new uncorrelated features from previously selected features. Then the hits from both tests were labeled and then merged together for training and testing. So the adhesive hits were labeled 0 and abrasive reactives were labeled 1. The training and testing data was then split into 2 for training and testing using an 85 to 15% ratio. 3 different classification methods were used: logistic regression model, which is a model that assumes a linear relationship between the features and is also used for binary classification. Then a k-nearest neighbor classifier was also used, which is when unknown vectors are categorized based on their distance to their k-nearest neighbor in the training data set. To choose the best k number, different numbers were tested, and then the one with the best classification accuracy and also best performance time was chosen. And in this work, 5 was chosen as the best k number. The third method used is a backpropagation neural network, which is a form of deep learning. And in this one, a 3-layer feed-forward network was used. We have the input layer, the hidden layer, and the output layer. So in this case, the backpropagation of the errors also allowed us to improve the behavior of the network. Now for the test results. First, a cumulative AE hits plot was first looked at. So from the AE hits plot, we can see that there is a difference in how the adhesive wear tests behave throughout the test duration compared to the abrasive test. So the adhesive is the one in red, and here we can see that first we found that there was 8,000 more hits for abrasive wear test than there was in adhesive wear test. And also, AE hits in adhesive wear test accumulated up to 25% of their total hits in a short period of time, this could be representative of the initial test period where you have the particles on the wear surfaces of the two materials colliding together and creating energy that is recorded from the AE sensor or by the AE sensor. And whereas for the abrasive wear test, 25% of the hits took longer for us to go 25% of the total hits, which is probably because of the fact that there was a lot more hits recorded during the abrasive wear test. Also, the graph shows that we can probably split the test into 2 for adhesive, but for abrasive, there are 3 different regions, which was chosen to mean that the first region is the running in region. The start here is the running in process, where you have the initial collision of particles. Then this is the bit that was actually like the prolonged sliding process, where you have the production of wear debris happening and continued collision of particles. Then when the test also settles down, the steady friction happens, steady state is reached, is this last part. Whereas for the adhesive test, we had the running in period and then we had the steady state period. There was no prolonged sliding in the adhesive test. For the classification, first the principal component analysis was done, and 8 AE features were initially chosen using hierarchical link clustering. And then these 8 features were then fed into the principal components algorithm on MATLAB. And these features actually created 6 uncorrelated features that accounted for 95% of the variance. So further classification then used this new 6 uncorrelated AE features for the classification processes. Now, the classification's accuracy was looked at by looking at the training accuracy and test accuracy, and also using a confusion matrix and receiving operating characteristic curve. The confusion matrix allows us to look at how the individual classes also predicted as opposed to how the whole model predicted overall. And the receiving operating curve is a way of visualizing the false positive rates against the true positive rate. The closer the AUC, which is the area under the curve, is to 1, the better the classifier. As seen here, the logistic regression is the one that's performed the least of all 3 classification methods. This is probably due to the fact that the logistic regression, as I said before, assumes that there's a linear relationship between features, but we know that in terms of the wear processes happening on the AE features, there will be more complex relationship between the features, which would not be considered in a logistic regression classifier. And in opposition to that, the k-nearest neighbor and the BP network, they both have above 96% accuracy, because they were able to actually learn all the different complex relationships between the AE features. The BP network would be a preferred network over the k-nearest neighbor, because for k-nearest neighbor, every time you have a new unknown vector to classify, you would have to do the whole process again and go through the training data. Whereas for the BP network, the network actually learns from the training data. It fully learns using the training data, so you don't have to actually go over it every time you want to classify again, which would also save time, because in a case where you have more training examples and more features, the k-nearest neighbor will be more time consuming than the BP neural network. And also it was found that the adhesive wear test is the least classification accuracy of 94% compared to abrasive wear test. When adhesive and abrasive wear happens, things such as plastic deformation and cracking and crack propagation that happens on the surfaces, there are processes that are similar to both wear mechanisms, which would then mean that there will be features that will have similar characteristics that would lead to the misclassification error. In conclusion, we concluded that the BP neural network is the best classification method to use for future work. Also, we were able to successfully classify the AE signals based on different wear mechanisms. And this shows that there is potential for us to actually then classify signals acquired during natural and artificial joint movements, which would then be able to allow us to be able to actually achieve the potential of actually diagnosing joint pathology such as osteoarthritis, low back pain, and also artificial joint failure. Thank you for listening, and any questions would be welcome.
Hello, Khadijat. Can you hear me?
Yes, I can.
I have a question. In your conclusion, you said that the resonant BP neural network is predictive accuracy. It is superior than the weighted Lewis labor algorithm. Have you examined what is the advantage? What is the cause make the BP neural network achieve better predictive accuracy? This is the first problem. And the second problem question is that can you briefly explain to me what is the principal component analysis? I saw this on the MATLAB toolbox of the machine learning toolbox in MATLAB, but I'm not very sure what is the application and what this function can benefit to our research. Thank you, Khadijat.
Okay, thank you for the question. So the first one, you said why BP neural network performed better than k-nearest neighbor. It doesn't actually perform better in terms of a large magnitude. As you can see, it's just 97% to 96%. So they both perform almost equally as well. So they're very good. So what I said was, in terms of the applicability, because what we want is a process that is going to be simple and dynamic. So because for k-nearest neighbor, it has this advantage that if you're going to introduce more examples, so here I use about 20,000 data sets. So if you're going to have up to like say 100,000 training examples, and you also want to increase to like say maybe about 20 features, with k-nearest neighbor, it's going to be time consuming because it's going to have to be going through the training data every time you want to classify a new one, because it is based on distances between the new data and the nearest data to that data in the training data set. Whereas for a BP neural network, it might take a while for the training to happen, but once you've trained a BP neural network, it fully learns everything about the features. So when it comes to testing, it doesn't take as much time to test a new data set. And as for what principal component analysis is, so it's a mathematical technique. It involves, you would have it's like taking a matrix, you do a covariance matrix, but basically the explanation is that when you have lots of different features for your training, sometimes you might have features that are correlated or too correlated that have similarities between them. So instead of using 100 features that would take a long time, by doing PCA, you can use it as a dimensionality reduction. So you can use it to reduce the dimension of your data, and you can also be able to extract features that would actually have an effect that would actually be necessary for your classification or your regression analysis, whatever it is you want to do. You'll be able to take the features that account for the high number of variants. As you can see, I had 8 features to start with, but I actually used 6 of them. So I didn't need the other 2. So I hope that explains better.
Okay, thank you. Thank you for your explanation. And we have two questions from two people. The first one is from Diana. Says, thank you for this presentation, and a couple of questions. How did the BEAR resources help in your work? And also, in your opinion, how long will it be until this type of tool starts being used in the hospitals? As is the first questions from the Diana.
Okay, thank you, Diana, for the question. Yes, so in terms of the BEAR resources I use, so when I do my test, the acoustic emission signals, it's a very large data set that I can actually save on my computer. So I usually save it on the research data store, which is a BEAR resource that I use. So that's how I use BEAR resources in my work. So I save all my test data in the RDS so that I can access it anywhere I want to use it later on. And then as for when I think it will be being used in the hospitals, it's still a long way, I think, because obviously we are still in the testing stage. We have to try it out and actually test it with patients. So it might still be a while before we can get to be able to use it in the hospital, but it is a process that is on the way there. And obviously with the new technological advancements, hopefully at some point in the future, it would be able to be used in the hospitals.
Okay, thank you. Thank you for the questions, and thank you for the answers. And another question from the Hirami, and it might be a stupid question, but could you explain about the input variables for logistic regression again? And or please give some examples.
Okay, so here, so thank you, Hiromi. So the input variables for the logistic regression is my data. So I had, in the end, had about 24,000 by 6 matrix data. But for the regression model, it uses a sigmoid function. And since I used it on MATLAB, so MATLAB has all the algorithms inbuilt. So now I just put in my data set and then everything, and then I input my data set, and that's all I have to do on MATLAB. Using the MATLAB HAP function is what I used. So you choose logistic regression, you input your data set, and it does the analysis for you. I hope that answers the question.
Okay, thank you. Thank you for the questions as well and the answers. We got another question from Daph. Does the AEG techniques require any special or expensive equipment that would make applications difficult?
So it does, you do need to have, so the equipment we need is an AE sensor, and you have different sensor sizes based on, depending on where you want to apply it to. So you have a big sensor. I use a very small sensor, like a nano size sensor, like 8 mil diameter. So it depends on what you want. You have different sensor sizes. You need a preamplifier, and then you need a computer and the system. But in terms of making application difficult, they're not, the first buy might be on the expensive side, but then because it can be applied to lots of different techniques and lots of different applications. So once you have one equipment, all you just need is to always have your sensor, your preamplifier, and you just connect to the same computer. So it's not, in the long run, it's not an expensive equipment in the long run, but maybe to acquire the first one, it might be costly, but then you just use that same one for different applications.
Okay, thank you for your answer, and thank you the questions from the DAF. So any other questions from our participants? Yeah, I guess we don't have further questions to you, Khadijat. And thanks for your post presentation. It's very interesting, and also it's excellent. Thank you. Thank you, Khadijat.
Thank you. Have a good rest of the conference and have a good day.
Thank you.